Welcome back, everybody. In this video, we'll be getting actually started on section 10.1 about the ellipse. So we just spent a little time looking at circles, which are what you get if you take this two-cone arrangement and make a cross-section of it with a plane parallel to one of the bases. If the plane isn't quite parallel to one of the bases, you end up with an ellipse. And so that's the focus of this section. Not so much at all in terms of what the cone looks like, but more uh, just the two-dimensional shape in and of itself. So the ellipse is defined in terms of a distance, kind of like the circle was. We saw that a circle has the property that all of its points are equally distant from a fixed point called the center. So what the ellipse is defined by is, let's say we have these 2 points, let's call them F1 and F2, and we want to consider all the points where the sum of the distances from F1 to a point on the ellipse, we'll call that X1 or just XY, the distance from F1 to XY plus the distance from XY to F2, that is constant. So what you're seeing here, the little two black line segments, the length of those two is the same as the length of the two blue ones taken together. Another way to kind of visualize it is in terms of how you could actually draw an ellipse, if you like. If you put 2 push pins into a piece of cardboard and then run a string between the two, and then use your pencil, you could trace out an ellipse. As the pencil goes around the ellipse ellipse is traced out. And of course, the length of the strings joined together is constant, right? So the sum of the distance from each of those 2 points where the push pins are to the ellipse itself is a constant. Those 2 points are called the foci. So, or each one is a focus. So some words here. Each one of those is called a focus. There's one of them. In order to make a plural out of it, that is more than one of it, it's F-O-C-I. And depending on who you ask, it's either foci or foci, and you'll hear both. Okay, and so I'll probably use both. And it's just a plural of focus, and it's just those 2 points. Another way of thinking about how an ellipse looks is if you were to take those 2 points, the 2 foci, and make them coincident, that is, be straight on top of each other, then you'd get a circle, right? The F1 to the ellipse length would be a radius, basically. So we're going to talk about something later called the eccentricity for an ellipse, and we'll revisit that idea at that time. Okay, so the geometric definition for an ellipse is, as we said, it's a set of all points in the plane, the sum of whose distances from 2 fixed points, called foci, F1 and F2, is a constant. Okay, so some terminology that goes with this, okay? I don't really test on words, right, terminology, but you're gonna need to know all this in order to do the problems, right? So if you have an ellipse, it's gonna have a center, just like a circle does, okay? So it's gonna have a center. And as with the circle, we'll call it HK also. And then, unlike a circle, which has one diameter all the way through, an ellipse has different lengths. If you look at the length of this ellipse, kind of the long way across, that's called its major axis, okay? The length, the short way across the ellipse is its minor axis. The endpoints for the major axis are each a vertex. So there's 2 vertices, that's plural of vertex. There's 2 vertices for an ellipse, and those are the endpoints of the major axis. Okay, the endpoints of the minor axis are called co-vertices. Okay, and then of course we have our foci in the picture as well. So major axis, minor axis, foci. Vertices are the endpoints of the major axis, and then the covertices are endpoints of the minor axis. All right. So next we're on to look at the equation for an ellipse. It turns out there's two equations for an ellipse depending on whether it's kind of wider than it is tall, like the picture you see here, or instead is taller than it is wide, like that. Okay, so on to the equation next. Okay, so the thing is that the way that the circle or the ellipse is defined, we could do its, derive its equation kind of like we did with the circle, right, using the distance formula. But it turns out there's significantly more algebra for this. But we can start it off, so at least. So the way that the derivation goes is you have this ellipse. This one's situated so that it's wider than it is tall. The first focus, it's all centered at the origin for convenience. Its first focus is at negative C0. The second focus is at C0. And so the length of those two blue lines are constant, the sum of those two. So the distance from F1 to P plus the distance from P to F2 is a constant. And it turns out in the algebra that it's more convenient to call it 2a, where a is a constant. Okay, and so what you see happening in the algebra that goes next is just an application of the distance formula. So the distance from F1 to P is that first radical, from P to F2 is that second radical. And then we go through a lot of algebra, like I said. For this, you don't need to be able to reproduce this. Although it's made out of things that you do know how to do, you know, isolate a radical, square both sides, multiply out binomials, add and subtract stuff on one side of an equation or another. So if you like, if you're interested, you can follow through the steps here. If not, that's okay, as long as you kind of recognize the definition for an ellipse is based on the sum of two distances being constant, and then you're going to need to know the equation that you get at the end, which is x squared over a squared plus y squared over b squared equals 1. Okay, like I said, the derivation for that whole equation pretty much a lot longer than the one for a circle, but we'll just mainly focus on the equation. Okay, so the table here, this one isn't a repeat from our textbook. It's taken from another textbook, and I think it's simpler than the one in our book. So let's take a look. So depending on which way the ellipse is oriented, that is it wider than it is tall, like in the picture on the left, or is it taller than it is wide, like the picture on the right? Okay, so let's go through all of the stuff. Remember that the picture on the left is the wide one, the picture on the right is the tall one. Okay, the equation for each is x squared over a squared plus y squared over b squared equals 1, or x squared over b squared plus y squared over a squared equals 1. Okay, so we want to try not to memorize too much here. So we want to make sure that we can understand as much as we can to cut down on the amount of memorizing that's needed. Okay, notice that there's a little restriction down here that a is bigger than b, which is bigger than 0. A and B are both positive, and A is the bigger one, okay? You know, you want your grade to be an A, not a B, right? So A is bigger than B, okay? And so taking a look at our picture, for the equation on the left, it's x squared over a squared, okay? Notice that it's bigger in the x direction, okay? A is bigger, okay? And this thing is wider in the x direction. On this one, the y squared is over a squared. This one, the bigger number is with the y term, and so this thing is bigger in the y direction. Okay, so I wouldn't sit and memorize these as two separate equations. I would just learn the one, x squared over something, y squared over something equals 1. And then remember that the bigger number is going to be under the direction for which it's wider, right? So when it was wider than it was tall, the bigger number is on the x. When it was taller than it is wide, the bigger number is on the y. Okay, and then just remember A and B. A is always bigger than B. Okay, so then moving on, where do the vertices have to be? Remember that the vertices are the endpoints of the major axis, right? And so on this one where it's wider than it is tall on the left, that means that the y coordinates have to be 0, right? Notice that these are both centered at the origin, okay? So if this thing's major axis is horizontal because it's wide, okay, it's wider than it is tall, that means that the x coordinates have to be opposites and the y coordinates have to be 0, okay? For the one where it's taller than it is wide, the major axis is along the y-axis. And so the x's have to be 0. If it's taller along the y-axis, then that means that the x coordinates have to be 0. Okay? Okay, the major axis is either horizontal or vertical, depending on the orientation of the ellipse, and its length is always 2a. Okay, the minor axis is the other direction, is either vertical or horizontal, and its length is always 2b. Okay, and then this formula is going to turn out to be useful for us to know. So this thing is important. Let me write that out here. That c squared is equal to a squared minus b squared. And where that comes from is actually, it turns out it's in this big long derivation, okay, that we kind of more or less skipped over. It's in there if you want to go read about it. But basically, the c is where the foci are, okay? The foci are at plus and minus c0. And so you can find out where the foci are going to be given a and b. All right, so that's pretty neat. And how to memorize that, at least how it worked for me, was I remembered kind of what the Pythagorean theorem was like, which was a squared plus b squared, only this is not that, so it's got a minus in it, okay? As long as you have some way to remember that, then that works for me. C squared is a squared minus b squared, and that's a formula that relates the foci location and the a and b. Okay, so let's try it out. Okay, so we've got this thing, this formula right here. It says find the vertices, the foci, the lengths of the major and minor axes, and then also sketch the graph. So let's try. So how we're going to want to do this first is, I noticed that on these equations, they're both set equal to 1. So if we've got a formula that looks like this, where it's set equal to 36, then what I probably should do first is divide through by the 36, so that on the right side we have a 1. Okay. All right, so 4 over 36, that's the same as 1/9. So we will have x squared over 9. And then x squared, or 18 over 36, is the same as a half. So we'll have y squared over 2. And then 36 over 36 is 1. All right, so there's kind of our standard form equation for the ellipse. So now we'll see about finding all the other stuff, and then we'll make a picture. Okay, so let me start or continue by getting the vertices next. The vertices are the endpoints of the major axis. So we should figure out whether this thing is taller or wider. So taking a look at the denominators, again, I didn't memorize this equation, right? A's and B's and B's and A's, okay? It's x squared over 9 plus y squared over 2, which is bigger, 9 or 2? Okay, 9's bigger, right? So this thing is going to be bigger in the x direction, okay? So the vertices are going to be bigger, it's bigger in the x direction. So the y coordinates on the vertices will be 0, and their x coordinates are going to be plus and minus 3. So plus or minus 3, 0. Okay, notice that you can get that from the equation by substituting in y is 0. If y is 0, then x has to be plus or minus 3. Okay, so we found the vertices. We should get the foci next. Okay, so foci, c squared is a squared minus b squared. Okay, so if you're worried about which is bigger, just remember that c squared has to always be positive, right? So just take the big one minus the small one. Okay, so that c squared is 7. So then the C is root 7. Okay, so at this point you got to ask yourself, well, how do I know if it's root 7, 0 or 0 root 7, right? Which one is it going to be? Remember that the foci are always going to lie on the major axis. Okay, back to the picture. The foci are always on the major axis. So when it's a wide one, the y coordinates are 0. When it's a tall one, the x coordinates are 0. Okay, notice that the vertices and the foci, where the 0 is, matches. For a wide one, the 0 is in the y's. For a tall one, the 0 is in the x's. Okay, foci are on the major axis. Okay, this one is wider than it is tall, so that means that it's plus or minus root 7, 0. Okay, so there's the foci. All right, so lengths of the major and minor axes. So I'm actually going to do that after I do the graph because it's going to be easier for you to see that way. All right, so let me get a graph for us going. It's a good idea generally to find out all your stuff, right? The vertices and all that stuff before you make your grid so that you end up with a decent looking picture. All right, so the vertices are plus and minus 3, 0. And then we didn't need the co-vertices in the original question, but it's a good idea to have them for our picture's sake. So let's go ahead and see what those are. Okay, the co-vertices are the endpoints of the minor axis, right? And so when x is 0, y will be plus or minus root 2. Right? You can get that by taking a look at the equation and letting the original equation and letting x be 0. When x is 0, what does y have to be? Okay, that'll be root 2, which is about 1.4 for my picture. Okay, all right, so that's good. Let me label some points. There's the vertices at 3, 0, and negative 3, 0, 0, root 2, and 0, negative root 2. Okay, for the co-vertices. Okay, rest of the question, the major axis length is going to be 6, right? It's twice the distance from the center out to one of the vertices. And then the minor axis is going to be 2 square roots of 2. Okay, off of the picture. All right, so that takes care of our first example involving an ellipse. Okay, so let's try a little bit more. So for this next example, we're just trying to find the foci. Okay, maybe if we're interested, we'll find some other stuff. Okay, once again, I'm going to need to rewrite this a little bit so that there's a 1 on the right side. So it's 4x squared plus y squared equals 16. I'm going to divide all three terms by 16. Okay, 4 over 16 is a fourth, so we'll have x squared over 4. Y squared over 16 is just y squared over 16. And then the right side is a 1. All right, so then this one, notice that the bigger denominator is with the y's, right? And so this one is going to be taller than it is wide, okay? As far as finding the foci go, it's still a squared minus b squared. And again, you don't have to worry about which one's the a, which one's the b. Remember that c squared always has to be greater than or equal to 0. And so, well, it's got to be the big minus the small. So 16 minus 4 is 12. So c is square root 12 or 2 root 3. Okay? And so here's where knowing what direction this thing faces will help us figure out the coordinates on this thing. So on this one, it's bigger in the y direction. Okay? I know it's bigger in the y direction. So that means that when we find the foci, their x coordinate has to be 0. So it will be 0 minus 2 root 3 and 0, 2 root 3. All right, that answers the question. We were supposed to find the foci. But just for fun and so that you have more examples, let me put down a few more pieces of information out of this ellipse. So the major axis, or let's go with vertices next. So the vertices, this thing is taller than it is wide, so there'll be 0 and then plus or minus 4. Okay, take a look back at the equation. When x is 0, y squared will have to be 16, so y will have to be plus or minus 4. Okay, so that will make it so that the major axis is what? It's going to be 8, right? And then the co-vertices, okay, those will come when y is 0. So when y is 0, x will be plus or minus 2. Okay, and so that the minor axis length is going to be 4. All right, so that just gives us a little bit of extra stuff. The original question just needed the foci, so we've got that. Okay, all right, so now this question is going to be kind of fun. What we're going to do is actually make the equation of the ellipse given some of the information out of it. So on this one, we're going to know the vertices and we're going to know the foci. And then from there, we're going to write down the equation. So the first thing I'm going to do is try to make a little sketch of this thing. And so let's do that. All right, so then I've got a little grid here for us to start working with our picture. I went ahead and put the vertices on. Those are going to be at 0 plus or minus 5. And then I didn't put the foci on yet. We can go ahead and do that now. So those will be at 0 plus or minus 3. If we didn't know the foci, then we wouldn't really know the shape of this thing at all, right? If I didn't tell you the foci, this thing could be kind of tall and skinny, or it could even be wide. Right, that looks really bad. It could even be really wide, right? So we wouldn't know what this thing looks like without knowing what the foci are. So fortunately, we know the foci here are at 0 plus or minus 3. So we do know that this thing is taller than it is wide. So it'll be x squared over y squared over, and there's a 1. Okay, so it's taller in the y direction. So the distance from the center to a vertex, that's 5. 5 squared is 25. Okay, so then the only other piece of information we need in order to finish this equation is to know what the denominator in the x direction is. And that's where knowing the foci is going to help. We know that c squared is a squared minus b squared. We know that c squared, c is 3, so c squared is 9. The a was the bigger number, that was 25. Okay, and so 25 minus b squared is 9, so b squared has to be 16. Okay, so that's how we're going to fill out the rest of our equation. It's going to be a 16 underneath that x squared. So to kind of recap what it was that we did, which it didn't take a lot of calculating, we knew where the vertices are. That told us that this thing is taller than it is wide. And so that I know that the denominator for y has to be bigger than the denominator for x because it's bigger in the y direction. The distance from the center to a vertex was 5. So 5 squared, or 25, will go in the denominator. Then we use the equation for the relate the foci and the a and the b to help us figure out what the b is. Okay, and that did it. Okay, so we are getting there. So the next part has to do with eccentricity on an ellipse, and that has to do with the shape. So ellipses can be almost flat, or they can be almost circular to where you can't really tell just by looking how elliptical it is. And to describe the roundness of a ellipse, we use something called its eccentricity, and there's of course a formula for that. So regardless of our formula, x squared over a squared or x squared over b squared, whichever it is, it doesn't matter. The eccentricity is called E, okay? And it's c over a. C, remember, is that number that's related by c squared is a squared minus b squared. And then it's divided by the a, the distance from the center to a vertex. Okay, before we go any further, I need to talk about the E thing. If you're looking at that E and thinking, okay, well, does this have to do with like the e to the x function and natural logarithms and stuff? No, it doesn't. This is like one of the few places where we use E in math and it doesn't mean this natural logarithms thing, E thing, exponential function thing. So it's just not, okay? Usually E is not used for anything else. This is one place actually where we're going to, E is going to mean eccentricity and not anything having to do with logarithms. So you can forget about that for right now. Okay, so E is C over A, where A is the distance from the center to the vertex, and C is the distance from the center to the focus. So it's, notice that this thing is going to be a proper fraction, right? Think about it for a second. The C is always going to be the distance between the center and a focus, that's C. And A is the distance from the center out to the vertex. If you think about it, the focus has to be inside the ellipse, okay? If the focus is inside the ellipse, which it is, then C has to be smaller than A, okay? If C is smaller than A, then this fraction right here, this fraction is always less than 1. Since C and A are both positive, it's got to be 0. So the eccentricity is always going to be a number between 0 and 1. The closer it is to 0, the more circular the ellipse is. The closer it is to 1, the more kind of flat it is. Think about it in terms of the picture. If the C is nearer the origin, nearer the center, the more circular it is, okay? If the C is more towards the vertices, the more kind of stretched out it is. Here are a couple of examples. This first one, E is 0.1. That's relatively small. This thing, if you don't look really, really carefully, it could look almost like it is a circle. E of 0.5, that should look a little more squashed to you. 0.68 definitely squashed, and then 0.86 definitely squashed. So the bigger the number for eccentricity, the more squashed it is. We don't have really a sense of like, okay, well, you could look at this ellipse and say, okay, well, its eccentricity is 0.7 or something by looking at the picture. Mostly, we would just judge which one is more squashed than the other based on calculating its eccentricity. All right, so let's just calculate the eccentricity for one of these. So it's 8x squared plus 9y squared equals 18. So we're going to want to, once again, put this thing in kind of this standard form equation so we can figure out what the A is and then calculate what the C is. All right, so let me begin by dividing the original equation by 18. Okay, so then we'll have a 1 on the right side, which is what we need. So 8/18, that will be the same as 4/9. Say it, then write it 4x squared over 9. I'll figure that out in a minute. 9/18 is a half, so we'll have y squared over 2. And then that's equal to 1. Okay, so then we need to know the C and the A. So this thing is not quite in the right form because the coefficient of x squared is a 4. And up here in these equations, the coefficients of x squared and y squared are all 1s. Okay, so I need to deal with the fact that down here we have a 4. So how we're going to do that is I'm going to take the left fraction and we're going to multiply by 1/4 in the numerator and denominator. So that's kind of a commonly used device to kind of change the coefficient on either the numerator or denominator of a fraction. So 1/4 of 4x squared will make that just a single x squared. And then 1/4 of 9 is 9/4. Okay, usually we don't like to see complex fractions in math, but here's a situation where we need it. So there it is. Okay, so now we need to know the eccentricity. Okay, is it C over A or A over C? Okay, remember that the A is the distance to a vertex, and so it has to be bigger, and so it has to be C over A. Okay, so the A here is 9/4, right? 9/4 is bigger than 2, right? So that will be, actually, we need the square roots of that, right? So the A is the square root of 9/4, which is 3/2. Okay, so the A is 3/2. And then for C, we know C squared is A squared minus B squared. So that's 9/4 minus 2, and that's 1/4. So then C is 1/2. Okay, 1/2 divided by 3/2 is 1/3. So this ellipse that we were given in the first place has an eccentricity of 1/3. Okay. All right, before we go any further, I wanted to show you a couple of pictures of some ellipses drawn on the computer. So here we've got an ellipse with foci at 0, plus and minus 1.890, and you should be able to see that the ellipse is relatively circular, and I've calculated also the eccentricity, and it's about 0.40. If we change it so that the A is bigger relatively, you'll see that this thing is more squashed looking. You'll see also that the foci are closer to the vertices now than they were a few minutes ago, and then that eccentricity is now calculated up here in the first row is 0.75. Okay, if we change the B, that will also change the squashedness of the ellipse. Now the foci are practically at the vertices, and the eccentricity is 0.93. So if we change that, the foci will get closer and closer to each other, and the thing looks more and more circular. If you think about it, if we make the foci right on top of the origin, then that's going to make A be it's going to make the A and B be equal to each other, and we'll end up with a circle. So I just wanted to show you a couple of examples of calculating the eccentricity and how that relates to the foci's relative position inside the ellipse. All right, before we go any further, I wanted to point out basically that circles are pretty much just special cases of ellipses. So far we've seen basically two forms of an equation of an ellipse. Here I've drawn the equation for the one that is wider than it is tall. If we have x squared over b squared plus y squared over a squared, that'll be one that is wider than it is, or taller than it is wide. If a squared and b squared are equal to each other, right, then what do we get? Okay, let's say that they're equal to each other, then x squared over a squared plus y squared over b squared could be called y squared over a squared if the two are equal to one another. And then the same thing can be said about the second one, so I won't write it a second time. If we have x squared over a squared plus y squared over a squared equals 1, then we could just multiply both sides by a squared. So we'll have x squared plus y squared equals a squared. This gives us basically a circle, right, with radius a, right? So this should illustrate that if the a and b are the same, then you end up with a circle. Okay, that takes us to the end of this video. We have just a little bit more to do on ellipses, and then we'll be all finished. So let me know if you have any questions in the meantime, and have a great day.